All right, so what does f prime say about f? In other words, what does our derivative tell us about the actual function? And to be honest, we'll also take a look at what the second derivative tells us about the function, because they tell us a lot about what's going on. And then we can use that information to do things like, I don't know, draw a graph. So one thing that f prime will tell us is it will tell us where a function is increasing and when it is decreasing. So if our derivative is positive, if it's greater than 0, then f is increasing. And if our derivative is less than 0, f is decreasing. And I write these as if then. It's actually bidirectional or biconditional. So it's true if we read it front to back, but it's also true the other way around. So if f is increasing, then the derivative is positive. And if f is decreasing, then the derivative is negative. So it works both ways. Not always the case in mathematics, but in this case, it is true. So if we know where we're increasing or decreasing, then we can find local minimum and maximum values. And a local minimum happens at an x value where the function values are less than anywhere else around that x value. So the local minimum refers to the y value of the function, but is described using the x coordinate. For instance, the parabola y equals x squared would have a minimum of 0 at x equals 0. Probably a bad example. If I did x squared minus 2, that might be a little bit easier. It has a minimum of -2 at an x value of 0. And then the local maximum is the x value where our y value is larger than any y values near that x. If we look at the second derivative, we can talk about concavity of a graph. Now, don't confuse concavity, you don't go to the dentist to take care of your concavities, okay? Concavity deals with, again, the shape of a graph. If the second derivative is positive, our graph is concave upward, kind of like a parabola. And the way that I think about it, concave up is U-shaped. And if the second derivative is negative, then we have a concave down or concave downward, kind of like the N in downward. So concave up looks sort of like a U shape. Concave down looks sort of like an N. Looking at a graph, it's usually pretty easy to tell where it's increasing and where it's decreasing and where we have a minimum and where we have a maximum. It's more difficult to tell where the concavity changes, where something is concave up as opposed to concave down. Mainly because it doesn't happen at, the graph doesn't change a lot when the concavity changes. And you'll see that throughout. Inflection point. This is just a point where the concavity changes. Anyone want to take a guess? What is the second derivative going to be at a point of inflection? That's at a point of inflection, it's not concave up, so it can't be positive. It's not concave down, so it can't be negative. That only leaves 0. Yeah, so where the second derivative is 0. All right. So as I said, some of what you'll do for homework for this assignment is, hey, here's a graph. Where is it increasing? Where is it decreasing? Some kind of basic stuff. Or you might say, hey, here is the derivative. Where is it increasing? Where is the function increasing and where is it decreasing? The other thing you'll do is, hey, here's a description. Let's draw a graph. So we're told that the first derivative is positive from negative infinity to positive 1, and it's negative from 1 to positive infinity. The second derivative is positive from negative infinity to negative 2, and from positive 2 to positive infinity, and it is negative from negative 2 to positive 2. And then we're also told that the limit as x goes to negative infinity is negative 2, and as x goes to positive infinity, we get 0. I'm going to write that down. Maybe you can read that, okay? Or should I go back to the single page? I can. Maybe. Right. So I'm gonna do that dual display so that I can see sort of what's going on and then graph it. So I'm actually going to start at the bottom. I know that as I go to negative infinity, I go to a value of -2. So that's a horizontal asymptote. And as I go to positive infinity, I go to a value of 0. Another horizontal asymptote. Unless I'm given information about a vertical asymptote or a place where the function has a hole, I will assume that the graph is continuous. Okay. So from negative infinity to +1, my graph is going to be increasing. And then from 1 to positive infinity, my graph is decreasing. So my graph might look like that. And now I should check concavity. And the truth is, if we do a good job with increasing and decreasing, concavity tends to take care of itself. So if I look at this, it says from negative infinity to -2, I'm concave up. It's not bad. And then from +2 to infinity, I'm concave up again. Yeah, that one might be off a little bit. And then from -2 to +2. So the only way that I could fix that, and again, is maybe like that. So notice the directions though, say, sketch a possible graph. So this is a possibility of infinitely many possibilities. But it meets those criteria. So for your assignment, problems 2 and 3, 10, 15, 16, 17, and 23. That page doesn't seem right, but I might be thinking of my BC calculus class. Yeah, that page is not right. Sorry, I was trying to put you 10 pages ahead of where we were. It won't happen again until the next time it happens, okay, I promise. All right. And so just, so you don't think I forgot about you. This is the review assignment. You're all saying, yeah, thanks, Mr. Gingrich. We wish you would have forgotten about us.